Hello there, this is a geometry video. It is chapter 8, section 7, and it is the last section in this chapter, and so you know that means that you will be having a test coming up very shortly. And today's lesson is about vectors. And a vector is basically something that describes both the magnitude and direction of a quantity. So for example, something like if you were to say speed, for example, is 10 miles per hour. That's only going to be a scalar because it's only giving you the quantity that it's 10 miles per hour. So that would be the magnitude, but it doesn't give you anything about direction. However, if you were to say that you were at a velocity of 10 miles per hour due north, now you're adding the 10 miles per hour is still there, but now you're adding the component of direction. So now you're talking about a vector. So a vector can be noted or annotated as kind of like a ray almost. A ray is an arrow that has two little tails here. A vector just has the first part of the arrow that goes up. You can also use a lowercase letter to call this vector A, or it's vector AB, or in the textbook when you're typing you'll see sometimes they'll use a bold lowercase letter. It's really hard for me as a teacher to write on the board bold, or for you as a student to write bold on your paper. So usually you only see this format when you're actually reading it in a textbook, but when you do your work, we're going to be using basically the little half arrow, if you will. So every vector has an initial point, kind of like a ray, or we can refer to the initial point as a tail. So this has an initial point of A, and then it has a terminal point, or what we call a tip, at point B here. So you'll see that's what a vector looks like, and then a couple of different ways of expressing of the notation for a vector. Again, lowercase letter, or you could use the initial and terminal points with the symbol above, also to indicate that it's a vector. Now for magnitude, the magnitude of a vector basically is the length of the vector. Okay, and so we denote that with these, they look like absolute value bars, but it doesn't mean that it wants the absolute value of AB, it wants the length of AB, the length of the vector AB. So when we use these bars, it's talking about finding the length of the vector, and we can do that by finding by using the distance formula, and we'll do that later on one of the examples. But I also wanted to indicate here the direction. The direction of a vector is expressed as the angle that it forms with the horizontal. So I want to kind of show you what I mean by that. So I'm going to draw in on this vector here the horizontal, just like so. And then we're talking about the angle. So again, it says that the direction of the vector is expressed as the angle that it forms with the horizontal between 0 and 90 degrees east or west of the north-south line. So there's two different ways that you can express it. You can express it as the angle that it forms with the horizontal, and if you do that, all we're looking for is this angle right here. And so that would be one way of expressing the direction of the vector. But another way of expressing the direction of the vector relates to the north-south line. In order to do that, you actually have to imagine, so I'm going to go ahead and take this off. So at that point, you want to imagine that you actually have an XY coordinate plane, so to speak. And you have that little guy and this little guy. And so of course we have north, south, east, and west as far as directions on a compass. And so at the same time now we're looking for the measurement between 0 and 90. So it's got so there's two different ways of doing the direction. One was the angle that it formed with the horizontal. We already talked about that. Another method of giving the direction is to have the angle, but the angle has to be between 0 and 90. And so it's basically between 0 and 90 east or west of the north-south line. This is what I mean by the north-south line. If you were to draw the north-south line there, then they're basically asking you for the angle that is either east or west of it. So in this case, it's going to be east because it's on this side. If it were on this side, we would say west. Okay, so now we're trying to find this angle here. So let's just say that this is basically, let's say that it's like 80 degrees or something. So then what we would say is that the direction of this vector is 80 degrees east of north. That's how you would say that. So that's how you do that. So now we want to go and start with our first example here, and it says use a ruler and a protractor. And I have all my stuff up here with me. I hope that I can help you do this. My protractor is more it looks more like a circle than anything, but it has the little half moon that you're used to, and it's got all my degrees here, and I can see through it, so it'll help me as I'm on the board. So it says use a ruler and a protractor to draw each vector, including scale on each diagram. So they want me to draw a vector M that is 15 miles per hour at 140 degrees to the horizontal. So in this case, we're not going to be using the north-south line. In part B, you can see this as west of south. So in part B, we're going to be using the north-south line. But for part A, we're just going to be using the horizontal. So I'm going to go ahead and draw my horizontal. So there it goes. All right, now the next thing that you want to do is this whole, it says include a scale. What it means by that is that you're going to have to say what your scale is going to be, because obviously we're not going to be able to draw 15 miles. It's going to be too long. So we want to do a scale. So I'm going to go ahead and say we can use a scale of 1 centimeter. So we're going to say that 1 centimeter, oops, we don't want to use, got to get my pen back. All right. So 1 centimeter is going to be equivalent to 5 miles. So 1 centimeter on my ruler is going to be equivalent to 5 miles. That means that I'm going to draw and label a 3 centimeter arrow, because I know that if 1 centimeter equals 5 miles, then for 15 miles I'm going to need 15 divided by 3 is going to give me 5. So, or sorry, 15 divided by 5 is going to give me 3 centimeters. So I'm going to draw my vector, and it's going to have to be 3 centimeters long. All right, so I have on my ruler here, I have my centimeters, 1, 2, 3. So I'm going to be using, I'm going to use inches because centimeters are too small. So I'm going to have, but you can use centimeters because on your paper, centimeters is going to be perfect. I'm going to use something different on the board because the board is obviously much bigger than your paper. So, but keep in mind that that's kind of what it means by including the scale. So as far as the 140 degrees goes, I need to take my protractor and put it over here in the middle of my horizontal, kind of lined up there. Here's 0 degrees, and I want to go 140 degrees. So 140 degrees is going to be, there's 105, 120, 135, so 140 is right here. I'm going to try to put a little dot there. Come on, pen. There it goes. So there's my little dot. And so it means that I'm going to draw three centimeters long. All right, and then this angle is 140 degrees. All right, this angle right here is 140 degrees. All right, so that's what it asks us to do, 15 miles per hour at 140 degrees to the horizontal. So that's basically all you have to do for part A. All right, so now we're going to go to part B. And in part B, you're going to need the northeast, west, south kind of situation happening. So let's do that first. Let's go ahead and draw in our compass here. So, oops, didn't get it all. I love when that happens. Come on, pen. Work with me. There we go. All right, so we're going to go north, south, east, and west, and this time it says 55 pounds of force at a 55 degrees west of south. Okay, so here is the south, and it wants to be west of south, so we're going to be over here. at a 55-degree angle. All right, but the first thing we have to do also is this whole 55 pounds of force. So again, we're going to be using a scale. I think that a good scale would be for us to use inches. So let's say that 1 inch, let's put that over here, 1 inch is equal to 25 pounds. If 1 inch is equal to 25 pounds, then you want to take 55 and divide it by 25, and you're going to get 2.2 inches. So when you draw your vector, you're going to want it to be 2.2 inches long. And again, you want to make sure that you use a ruler to measure that out. I'm not going to be as exact on the board because obviously my inches will be too small for you to see them. So I'm going to have to draw a little bit bigger. But what you're looking for is a 2.2 inch arrow that's 55 degrees west of the north-south line. So what that means is that I have to grab my protractor again, and I want it to be 55 degrees west. So I want it to be basically going in this direction 55 degrees. So I am going to go ahead and put my compass right here, and I want to do 55 degrees. Now, my compass is kind of different than yours, obviously. So I have to basically take right here, I'm looking at 270, but what I want to do is 55 degrees this direction. But these numbers are getting less and less and less. So in order for me to know what number I should be at, I'm going to go 270, and I'm going to subtract the 55, and it's going to be at 215. So 215 is right about here. And so you can use your protractor. Yours is a little different than mine. But basically you have to get that angle to be 55 degrees. And then you're going to draw your arrow 2.2 inches long. Don't forget that. Starting from right here. That's probably a little bit too long. So let's just kind of go like that. That might be, again, this is a lot longer than 2.2 inches for me. But again, I have to make it a little bigger so that you can see it. But again, you want to draw this 2.2 inches long, and 55 degrees west of south means that it wants to be on the west side of the north-south line. Okay, so I hope that makes sense to you on how you're going to draw those little guys. So now we're going to ask you to do this example, and then we are going to go to our next topic, which is vector addition. And vector addition, there's actually basically two ways that you can do this. And the idea, one of the ways is a parallelogram method, and the other way is a triangle method. And you can use whichever method is you like best. I don't think it ever actually indicates which way you should do it. But vector addition is kind of interesting. I'll show you the parallelogram method first. But basically, when you add two vectors together, the answer is basically the resultant vector when you put them together. So basically we have the parallelogram method, and remember that we said earlier that the initial point is the tail. Now that sounds weird because we think of tail end, but the initial point is actually the tail, and the terminal point is the tip. Okay, so remember that the initial point is the tail and the terminal point is the tip. In the parallelogram method, what you do is you want to basically put the tail of one vector to the tail of the other vector. You have them tail to tail. All right, so what I'm going to do is I'm going to basically show you what them. You want to transit them, so you want to basically kind of move this. Right now they're not actually touching, but you want to take your blue vector, basically something like that, and put them tail to tail, kind of like this. All right, and so then what you do is you basically create a parallelogram. So this is the parallelogram method. You would basically kind of draw an imaginary parallelogram. So I'm going to use my dashed line here. like that. And then this guy would be kind of like this. So you have a parallelogram. And then the resultant vector is when you find the diagonal that goes from where the two tails are touching to the opposite corner. So this would be your resultant vector when you add them together. This green line is A plus B. All right? So here you have your A and your B. So basically what it does is it basically gives you the idea that if you're going to add them together, imagine that you were walking this way for a while, and then all of a sudden you decided to walk this way. The point is that at the end of the day, you're going to end up at this spot. And what this green vector is indicating is that basically, what if you would have, instead of going two separate directions, what if you would have just gone straight from here to there? That's basically how that kind of works. So that's your parallelogram method, that you want to always put them tail to tail, and then the diagonal from where the two tails meet to the opposite corner. All right, and then you have a triangle method. The triangle method is when you take the two vectors and you put them tail to tip. So in this case, you put both tails together. In the case of the triangle method, you would put tail to tip. So that would be, the triangle method would take this blue A vector, and this is my tail and my tip, and then I would take the red vector, and instead of putting it tail to tail, which would be here, tail to tail, I'm going to put it tail to tip. So here's my tip, and I'm going to put my red vector at the tip of my other vector. So in this case, you have tail of the red to the tip of the blue. And so then your resultant vector, it would still end up being the same thing as the parallelogram method, but your resultant vector would also go from the tail to the tip of what would now form a triangle, which is why it's called the triangle method. So either way that you do this, you are adding the two vectors together. So the length of this little guy is the same as the length of that little guy. Parallelogram method, triangle method. In the parallelogram method, you want to go tail to tail, and then draw your parallelogram, and the diagonal from where the two tails meet to the opposite corner. In the case of the triangle method, you want to go from tip to tail. So you want to put the tip of the vector with the tail of the other vector, and then you want to go again tip to tail to form a triangle to get your resultant. Alrighty? So now we're going to do the examples. It says here in example 2, copy the vectors, then find vector C minus vector D. And you're probably thinking, oh my goodness, we didn't talk about subtraction. Well, it's not a big deal. Subtraction is the same thing as adding a negative or adding the opposite. So basically what we're going to do with example 2 is we're going to take, when you add these together, we're going to do vector C plus the opposite of vector D. So the opposite basically means that it's going to go in the opposite direction. So instead of having vector D going in the north direction, the opposite would be to go in the south direction. So we're going to do vector D basically like this. This is opposite D, and going in the opposite direction. Same length, but opposite direction. So now we can try whichever method you'd like. I'm going to go ahead and do the, I'm going to do the triangle method. Okay, and so the triangle method says to take tip to tail. So I'm going to take my blue vector, and I'm going to try to get it to be the same size. Of course, I'll just measure it here. It's about 10. So I'll come over here, and it's about 10. So there's my vector. There's my C vector. And then if I'm going to add it to my negative D vector, I'm going to add it to this guy right here. So I'm going to put tip to tail. So I'm going to put the tail of this vector on the tip of this vector. So I'm going to come over here and measure this little guy. It's about 8. So we're going to come over here and do about 8. All right. So now all I have to do for the triangle method is to connect I already did my tip to tail, so now I'm going to do my tip to tail here, and this is going to be my resultant. This guy right there. So there's my diagram. That's using the triangle method, but if you want, you could even do the parallelogram method, but it would be the same thing. So I would take, in that case, I'm going to go ahead and do it here instead of redrawing vector C. The parallelogram method is to take this vector and then put my negative D vector tail to tail. So I'm going to put that right here. We said it was about 8, right? So we're going to go, oops, wrong color. Want to go with the red here. We're going to go about 8 right there. And this time we're going to draw our parallelogram. So to do that, we're just going to do again, we're going to go, this is about 10. And then at about 8. There's your parallelogram. And remember that when you draw the resultant, you want to be where the tails meet to the opposite corner. So there would be our resultant. So you don't want to go this direction. You want to do it from where the tails meet to the opposite corner. Alrighty? So that would be the triangle method or the parallelogram method. So now we're going to ask you to do this example. Remember that this one's normal, C plus D. In this case it says D minus C, so in this case you would start with the D vector and then add the opposite of C. Alright, so remember that you're using the same vectors that were given in example 2. Alright, so now we're going to talk about standard position. A vector is considered to be in standard position if the initial point is at the origin, so 0, 0. And so that's what you can see right here. This is my initial point, 0, 0. And then, if that happens, you can basically talk about the component form. You can uniquely describe the vector when it's in standard position by the x and y coordinate, because that would give you where its location is. So that standard position is when the initial point or the tail is at the origin, and the terminal point would be the coordinates x, y. To describe a vector that is, because not all vectors will be in standard position, so you can use component form to describe a vector that is not starting at the origin, where the initial point is not starting at the origin. And component form, you'll notice that it has these funky looking brackets. They kind of look like arrows. So that's not to be confused with coordinate notation, which is parentheses. So component form, just in a nutshell. Your initial point would have the coordinates x1, y1. So notice the parentheses, it's just x1, y1. Your terminal point, so point P in this case, so in this case, the initial point would be 0, 0. In this case, the terminal point would be x, y. So you have x1, y1 for your initial point, x2, y2 for your terminal point. If you want to find the component form, all you want to do is now when you're using component form, you want to use the brackets here, the funky little brackets, and you want to say the difference in the x's. So you want to go x2 minus x1 for the x coordinate of component form, and you want to go y2 minus y1 for the y coordinate of component form. All right, so we're going to have you try that in this example. It says write the component form of CD, and then for the do-it-yourself question, you'll be writing the component form for PQ. So CD is the red vector here. So the first thing we have to do is have the coordinates, and so I've got that for you here. This point here is 0, -1, so that's the initial point. So we're going to call that x1, y1. And then over here at D, we have the coordinates are 4, 1, so we're going to call that x2, y2. And so for component form, we want to take the x2 and subtract x1, which is 0. And for the y coordinate of component form, you want to take y2, which is 1, and subtract y1, which is -1. All right? So then that becomes 4 minus 0 is just 4. And then 1 minus -1 is actually going to be 1 plus 1, which then becomes 4, and 1 plus 1 is 2. So my component form for example 3 is x coordinate 4 y coordinate 2. So it's not very complicated. So now if you will do the component form for PQ, we'll go on to the next example. In example 4, we are now going to get into the distance formula that I mentioned earlier, and also using a little bit of trigonometry to find the direction. So it says here, example 4, find the magnitude, which is the length of the vector, and the direction of vector r, which has component form -4, -5. So -4, -5, the first thing we want to do is to basically place our vector in the coordinate plane so that we can see what's happening there. And so I'm going to do that. So x coordinate is -4. So -1, -2, -4 is right here. And then -5 is way down here. So we're going to be right about, let's see here. I want to do this correctly. There's -5. And the -4 is right here. So we're going to be right there. And starting from the origin to -4, -5. All right, so there's my vector. And so to find the magnitude, remember the symbol for magnitude is going to be like that. The magnitude is basically they want us to find the length or the distance of this vector. So we can use Pythagorean theorem and basically the distance formula to find this, because we know that the distance here is 4 units, and the vertical distance here is 5 units if we were to draw an imaginary triangle here. Alright, so if you have a right triangle like that, this is basically 4 units and this is 5 units. So, my 5's all funky there. So I can do, the distance from is going to be 4 squared plus 5 squared equals hypotenuse squared, right? So to find the magnitude, I'm going to go ahead and, but that's only because it's starting at the origin. So another thing that you could do is for the distance formula, is this coordinates here are 0, 0. And the coordinates here obviously are -4, -5. So you can also use the distance formula. So either 4 squared plus 5 squared equals hypotenuse squared, or you can use a distance formula. I'm going to go ahead and use the distance formula so that you can have that should the problem not be in standard form or whatever. So we're going to go square root of x2, which is going to be -4, minus x1, which is 0. And then we're going to go -5 minus 0. And you're still going to end up with the same thing I said earlier, which is the 4 squared and the 5 squared. So you're going to get 16 plus 25, and 16 plus 25 is going to be 41. So the magnitude of this vector is the square root of 41, which is approximately 6.4. That's the magnitude. Now to find the direction, we said before, the direction is basically going to be the angle that is formed with the horizontal. All right, and we can see that the horizontal in this case is going to be the x-axis. So what we're looking for is for this angle right here. I'm going to go ahead and draw it in with a theta. We know that this right here is 180, and then we need to add to that this angle measure, and then that will be the direction. So I need to find this angle measure, and I can do that because if this is the angle, we know the opposite side is 5, and the adjacent side is 4. We don't know the hypotenuse. Well, we know now that it's 6.4, but we don't want to use the hypotenuse. We're going to use tangent of theta is equal to opposite over adjacent. So the opposite side is 5 and the adjacent side is 4. And we know that to solve for theta, we have to use the inverse I love writing and it not being there, okay? So we have tangent inverse of tangent theta equals tangent inverse of 5/4. So here the tangent and the tangent ends are going to cancel.